Today we will be presenting a proposal for the plant vascular graft, a plant-derived vascular conduit designed to replace diseased arterial segments and reduce restenosis. So today we will be getting into the background and significance of this, a graphical abstract, quick research summary, some of our research methods, and our solution potential. Atherosclerosis and plaque buildup progressively narrow major arteries. As plaque grows, blood flow diminishes, which increases the risk of heart attack, stroke, and organ damage. Plaque-related coronary artery disease is one of the most significant contributors to global mortality, accounting for approximately 9 million deaths per year. Current clinical interventions, such as angioplasties and stenting, can reopen these narrowed arteries, but they are not always durable. Up to 30% of patients who receive a bare metal stent will experience restenosis within the first year. Restenosis is the re-narrowing of an artery after treatment, usually caused by smooth muscle overgrowth and new tissue formation inside the vessel. This reoccurrence often requires repeat procedures and increases the risk of long-term complications. These limitations highlight the need for a new type of graft that can restore blood flow while reducing the biological triggers that cause restenosis.
So now that we've talked about atherosclerosis and restenosis, we'll be moving on to our research summary. So instead of using a stent here, we want to replace the damaged or diseased segments of the artery instead of trying to reinforce it. The way we could do this is by using a plant-based scaffold because depending on the species, it helps with stability and provides great scalability. And for native artery mimicry, you can use a perlecan coating and perfusion conditioning through a bioreactor. Moving on to our graphical abstract, we have the first artery here with restenosis. Then you would move on to finding your plant-based vascular scaffold, and you would coat it and condition it in the bioreactor. And then after implanting it, you would get your restored flow, reduced inflammation, and you would have that lower restenosis risk.
Now I'll walk us through the key components of the proposed methodology. So first, plant tissues are decellularized to remove all cellular content while preserving the native vascular architecture. This creates a natural biocompatible scaffold that mimics the branching and structure of blood vessels. Then the scaffold is coated with perlecan, a hairpin sulfate proteoglycan known to enhance endothelial cell attachment and improve early surface stability. Human endothelial cells are seated onto the scaffold to create a functional, living inner lining. Then the constructs are placed in a perfusion bioreactor where pulsate flow is applied to mimic physiological shear stress. This conditioning step promotes endothelial alignment, strengthens cell matrix interactions, and helps achieve physiological compliance. And then finally, the grafts would undergo in vitro testing to evaluate long-term performance. Together, these methods support the development of a graft that could maintain vessel patency and reduce restenosis-related failure models.
So, our solution has the potential to make a real impact in healthcare. First, by replacing the plaque-damaged section of the artery instead of adding another stent, we can restore normal flow and reduce the abnormal shear stresses that usually trigger restenosis. Second, because the graft forms a stable endothelial layer and uses a perlecan coat-coated plant scaffold, it lowers inflammation and thrombosis compared to metal implants. That gives patients who struggle with repeated stent failure a much better long-term outcome. And finally, the material source is a low-cost and scalable one. If this approach moves into preclinical and eventually clinical use, it could offer more accessible and biologically active alternatives to stenting, especially for small-diameter vessels where current options fall short.
And then these are our references, and in conclusion, we propose that plant vascular grafts are the solution to this issue.